Hello students. So the last class I have told you about your Bohr's atomic model, one of the important long question from your board point of view, and we have derived the radius of nth orbit and energy associated with electron present in nth orbit. So now we shall discuss about your dual nature of matter. Okay, dual nature of matter, very interesting topic. Okay, just focus on it, that is dual nature of matter. Dual nature of matter, or you can say particle and wave nature of electron. Particle and wave nature of electron. Okay, so all material particles, all material microscopic particles, you can imagine. Microscopic particle means it can be your electron, proton, neutron, even atoms and molecule also. Okay, so these microscopic particles, when they are in motion particularly, possess both the characteristics, that is your particle characteristics as well as your wave characteristics. Okay, so by considering these two characteristics for the electron which is in motion, this is called the dual nature of electron. Okay, so the material particles, and this concept was given by your de Broglie, and by considering these two characteristics, that is wave characteristics as well as particle characteristics of electron, he particularly considered another two scientists he followed, that is the Planck's equation. He used Planck's equation and your Einstein's mass energy relationship. By considering these two relationships, he personally derived an equation that is called de Broglie's equation. Okay, so let us derive how we get de Broglie's equation by considering both Planck's equation and your Einstein equation. Okay, so he suggested de Broglie suggested that all the material particles, generally microscopic particles, that is microscopic particles like electron, proton, neutron, atoms, even your molecules also, molecules, etc. possess both particle nature and wave nature. Is that clear? Particle nature as well as your wave nature. So he considered both the equation, that is Planck's equation and Einstein's mass energy relationship. He derived an equation which based on the above two characteristics and is known as and is known as de Broglie's equation. De Broglie's equation. Okay, so how he derived? According to Planck's equation, as you know, E that is equal to h nu, 1 photon h nu, and this h into nu is equal to c by lambda. This is equation 1. You know this h is your Planck's constant and lambda is your wavelength of electron. Okay, next, according to your Einstein's mass energy relationship, energy that is equal to mc square, where m is the mass of electron and c is the velocity of light. This is equation 2. Okay, so what we got if we compare this equation 1 and 2? Now by comparing equation 1 and 2, by comparing equation 1 and equation 2, what do we get? That your mc square that is equal to hc upon lambda. Okay, so 1c cancelled over here, so that implies mc that is equal to h by lambda. That implies lambda that is equal to h by mc. This is mass and this is the speed of light or velocity of light. So mass into velocity, you know, that is known as momentum. That is called your momentum. Okay, so this particularly this equation 3, this equation 3 is known as your de Broglie's equation. Equation 3 is known as de Broglie's equation. Is that clear? And you know this mc is nothing but your momentum, mass into velocity, that is known as your momentum. So lambda can be written as h by p, where p is your momentum and h you know that is Planck's constant 6.62 into 10 to the power minus 34 joule into second. This is your Planck's constant. Okay, now what this equation says, this lambda is equal to h by p, also another form of your de Broglie's equation, and this lambda is inversely proportional to this p mv. From this equation, what can I write? If you know this lambda is equal to h by mc, that means for a lighter particle m, if the mass is very less, for a lighter particle moving with a velocity c, instead of lambda is equal to h by mc, I can write also lambda is equal to h by mv. Okay, where mv is mass into velocity known as your momentum. Okay, so I can write over here, for lighter particle moving with velocity v corresponds to smaller d Broglie's wavelength, smaller d Broglie's wavelength. Again you can compare with this momentum also. Okay, so that implies more the momentum or speed of the particle means electron, okay, particle, shorter will be the de Broglie's wavelength. Very fundamental, very mathematical derivation is there. Now you know the relationship between this momentum and kinetic energy. We can correlate the momentum with kinetic energy also. How? You see, as you know, this lambda, the de Broglie's equation we have got over here, that is lambda is equal to h by mc or mv or simply p, that is p stands for momentum. We have got it. So if I know the kinetic energy, हमें कौन जानी चो? The kinetic energy, that is equal to half mv square. Okay, so can I write m square v square upon 2m? No problem. So this m square v square, that is the whole square of mv by 2m, and this product of mass into velocity, that is nothing but your momentum, p square upon 2m. Okay, so kinetic energy, that is equal to p square upon 2m. That implies p, that is equal to 2 kinetic energy into m, the root over. Now you substitute this, the value of momentum in terms of kinetic energy over this equation. Okay, so we will get lambda, that is equal to h by 2 kinetic energy into mass root over of this one. This is also your another form of de Broglie's equation. Clear? Okay. Now we will see about a numerical on this de Broglie's equation. Okay, suppose a question is like this. So here you see, calculate the momentum of a particle which has de Broglie's wavelength this much. That means your lambda is given to you 2.5 into 10 to the power minus 10 meter. Okay, so calculate the momentum of particle. You know that lambda is equal to h by p. So you have to calculate this momentum p that is equal to h by lambda. So value of h, you know, 6.62 into 10 to the power minus 34 joule into second, divided by that is your lambda is giving you 2.5 into 10 to the power minus 10. So its value, that will be found to be 2.64 into 10 to the power minus 24. Okay, so this one is the momentum. So that will be this one, mass into velocity, meter per second, kg. So this one in SI unit, this will be kg meter per second, kg meter per second. Okay, so very simple numericals are there based on this just relationship, that is lambda is equal to h by p. Here you see, the question is like this: what is the mass of a photon? Okay, what is the mass of a photon of sodium light with wavelength of this much angstrom? Mass of a photon. So you know lambda, that is equal to h upon m into c. So that implies mass you have to calculate, m that is equal to h by lambda into c. So value of h is 6.62 0.62 into 10 to the power minus 27 org into second, because you know 1 joule that is equal to 10 to the power minus 7 org. Okay, and that's 10 to the power minus 34 was that. So you just multiply 10 to the power minus 7, that will be org into second, because everything is given in CGS unit, divided by this lambda is given you 5890 angstrom, convert it into centimeter, minus 8 centimeter, into what is the speed of light, 3 into 10 to the power 10 centimeter per second. Okay, just calculate it, and its value found to be here 3.752 into 10 to the power minus 33 gram. So this one will be its answer. Okay, clear? So next we will discuss about your Heisenberg's uncertainty principle. Okay, Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. So what he suggests, that it is completely against your Bohr's atomic model. You see, according to Bohr, electrons are revolving in well defined circular orbits around the nucleus. But what Heisenberg found, that electron is nothing but a wave. The motion of electron is just like wave, like that of radiant energy. In electromagnetic radiation we have studied. So here, for a electron like microparticles, okay, due to its wave nature, it is almost impossible to predict its position and momentum simultaneously. Okay, if you see, if an electron is moving, this is according to Bohr, it is moving in well defined circular orbit. This concept was given by Bohr, but Heisenberg's principle was totally against of it. Due to wave nature, the electron can move like this, like this. Okay, if electron move in this way, then tell me, is it possible to predict its position as well as momentum simultaneously? Can you predict more precisely its velocity or momentum or its position? No. So exactly this information was given by him. Okay, so what he said, that is, it is impossible to measure simultaneously the position and as well as the momentum of an electron. It is impossible to measure simultaneously the position and the momentum of an electron. Okay, so mathematically what he suggests, del x into del p is greater than equal to h upon 2 pi. H upon 2 pi. Sorry, this will be equal to h upon 4 pi. Okay, so where this del x is your uncertainty in position, or you can say error in position, because the position is not fixed. electron may be here, may be there, may be there, may be here, may be here. Okay, there is no specific position for such a microscopic particle which is moving in wave nature. Okay, like that of a radiant energy or electromagnetic radiation. So it is very difficult. So del x, that is your uncertainty in position, or you can say error in position, and your del p, that is equal to uncertainty in momentum, or you can say error in momentum. So its limiting value I have written over here, del x into del p is greater than equal to h by 4 pi. Its limiting value can be how much? Del x into del p is equal to h by 4 pi. Okay, somehow you can also written like this, del x into del p is greater than equal to h cross by 2. This h cross is equal to h by 2 pi. This is also another form of your Heisenberg's principle. Is that clear? So del x into del p is equal to h by 4 pi. It cannot be less than that. Okay. So how? If you imagine this del x is specific, suppose you mention the position is specific. If the position is specific, then the momentum will be not specific. It will be uncertainty. If you imagine this position has some certainty, then this del p will be uncertainty. So that it will be equal to, product will be equal to always a constant, that is h by 4 pi. If you imagine that the momentum is specific, then the del x will be not specific. Suppose this one is nucleus and this one is an electron. Okay. Suppose this electron absorbs any radiation, then it goes from this state to higher energy state, and you see, suppose the electron is here. If the position of electron is here, okay, so can you tell me, since it absorbs certain amount of energy, definitely its momentum will be in any direction. Momentum is not specific. Its momentum, due to absorbing energy, its velocity will change. It may move towards any direction. So direction is not specific. So if position is specific, then momentum is not specific. Okay, that's why this equation can also again written as this del p can be changed like this. Okay, so what we have got over here? The Heisenberg's uncertainty equation, that is del x into del p is your change in momentum, that can be written as del mv. So mass is constant, so it will be like this, del x into mass will not change, m into del v, that greater than equal to h by 4 pi. Okay, so that implies, so this is another equation. I can write del x, that is equal to del x is greater than equal to h by 4 pi, del x into del v is greater than equal to 4 h by 4 pi m. This is also another equation of your that is Heisenberg's uncertainty principle. That clear? Now you see, if the velocity or speed, that is momentum, will be here, then tell me, if momentum becomes 0, that means if momentum is fixed, if momentum has some certainty, then you tell me the value of del x will coming out to be infinity. That means I can write over here, if del v is equal to 0, then del x will be infinite. And it's vice versa. If del x is equal to 0, then del v becomes infinity. Del v becomes infinity. So this is totally the contradiction of a Bohr's atomic model. According to Bohr's atomic model, electron, there is a central positive charge core nucleus at the center, and electrons are revolving, that is their planetary motion I am saying. Electrons are revolving in well defined circular orbits, but here this is completely opposite. It is very difficult to measure its position and momentum of electron like microparticles which are in motion. Okay, so this was almost opposite, almost contradiction of your Bohr's atomic model. Okay, so now let us discuss one or two numericals based on this uncertainty position and uncertainty momentum. Okay, students, you see here the question is, calculate the uncertainty in velocity of a cricket ball of mass 150 gram if the uncertainty in its position is of the order of 1 angstrom and the value of Planck's constant h is given you 6.6 into 10 to the power minus 34 kg meter square second inverse. Okay, so what you have to do over here, that is, you see, calculate the uncertainty in velocity of a cricket ball of mass 150 gram if the uncertainty in its position is of the order of 1 angstrom. So it is given in MKS unit, Planck's constant, so you just convert the mass. Mass is given you 150 gram, so convert it into kg, that will be 0.150 gram. Am I right? Because this is in gram, you have to divide 10 to the power 3, then you will get 0.150 gram. Okay, so next data are given to you. That is formula lambda is equal to calculate uncertainty. So principal is our del x into m into del v, that is equal to limiting value we can apply greater than equal to, you just apply equal to, that is h by 4 pi. You have to calculate uncertainty in velocity, that means del v you have to calculate. So del v, that is equal to h by 4 pi into m into del x. So the value of h is 6.6 into 10 to the power minus 34 kg meter square second inverse divided by 4 into 3.14 value of pi into mass 0.150 gram. Okay, oh sorry, 15 kg into del x, position is given you 1 angstrom. 1 angstrom is equal to how much meter? 10 to the power minus 10 meter. Okay, 10 to the power minus 10 meter. So you just calculate the value, that is coming out to be 3.499 into 10 to the power minus 24 meter per second. MKS unit, meter per second. Okay, so these are the simple numericals based on the formula basis numericals, just do it. Okay, so students, now we will discuss, you can say, another important long question from your atomic structure, that is quantum numbers. Okay, we will discuss quantum numbers. Quantum numbers, very important, quantum numbers. Okay, suppose you need to search a person in the world. Okay, suppose you need to search a person in world. So what are the conditions, or what are the necessary things over here so that you can find out a person, unknown person or known person you can say in the world. So first you know from which country he or she belongs. Am I right or not? And if you predict the country, then you have to focus in which city of that country, Next you have to know the track or road or street connected to that city also. Okay, the street to that city. Okay, and the final one, that is house number. Then after that you can find out that person. Am I right or not? Suppose you need to find out this guy. This is, let's say, Francis. You need to find out Francis. Okay, so from which country? This is America. From which city? Let's say that is Washington. Okay, and the street to Washington, and next one is his house number. Okay, then you just make it, hello, this Francis will come to meet you. Okay, you have got Francis. Like that up, I am comparing this Francis with electron. Where is actually electron lies? Where is the position of electron? Although we know it's a microscopic particle, and according to Heisenberg, its position cannot be predicted, but still we can predict the probability of finding electron where the electron density is maximum. Okay, so there are certain numbers which are used to find out the density of electron, you can say, or the position of electrons. These numbers are known as quantum numbers. Such numbers are known as quantum numbers. Okay, so these are the identification numbers. The identification numbers which are required to locate the position of electron. The position of electron are known as quantum numbers. Okay, such numbers are similar to the address of a person, just I have explained. Okay, so what are these quantum numbers we need to discuss over here? First one, that is principal quantum number. Next one, that is azimuthal quantum number. Okay, next one, that is magnetic quantum number, and the final one, that is spin quantum number. Okay, so let us discuss one by one to find out where actually maximum electron density is found, or where is the position of electron actually. Okay, these are few identification numbers, or you can say this principal quantum number, azimuthal quantum number, and magnetic quantum number. These are the solutions observed from Schrödinger wave equation, that is out of our syllabus. I don't need to discuss over here. Strictly we will go through these quantum numbers one by one. Okay, so first one, that is principal quantum number. Okay, so very easy points are there. In Bohr's atomic model, you know, electrons are revolving in circular orbits or energy levels. These levels were designated as KLMN. So such KLMN will be represented by this principal quantum number. Okay, it represents it represents the main energy level or cells in which electron is revolving, in which the electron is revolving, in which the electron is revolving. Electron is revolving. It is designated by, it is designated by your n. Okay, so this n, that can be 1 2 3 4, you know, for K cell, L cell, M cell, N cell, etc. Okay, so principal quantum number actually represents the main energy level or cell in which electrons are revolving. Very easy, at a cell ko hi represent kurchi. Okay, so you have considered this one is nucleus and this one is K cell, this one is L cell, this one is M cell. So here that is n is equal to 1, n is equal to 2, n is equal to 3. So these are principal quantum numbers. Okay, next, the number of electrons present in a cell is given by the formula, you know, that is 2n square. 2n square. Okay, so for K cell, tell me, for K cell n is equal to 1. So number of electron 2n square, 2 into 1 square, that is 2. Similarly, for second orbit L cell, n is equal to 2. Number of electron, that will be 2 into 2 square, that will be 8. For M cell n is equal to 3. So number of electron, that will be 2 into 3 square, that will be 18. Okay, likewise. So this is about your principal quantum number. Easy. It represents the cell or main energy level in which electron is revolving. Okay. So next we will go through your azimuthal quantum number. Okay. Azimuthal quantum number. Second one, that is azimuthal quantum number. First one, cell. Next, this azimuthal quantum number represents subcell, like that of head post office, sub post office. Okay, likewise. So this because we are moving towards electron, actually where we are searching the position of electron, where actually it lies. First one we have felt in macroscopic level, that is cell. Then we should go through your subcell, that means we are moving towards electron. Okay, to find out its position, to find out not exact position, but the density of electron is probably maximum. Okay, so first one, that is principal quantum number, we have covered it, which represents your main energy level. Right now, the second type of quantum number, that is azimuthal quantum number. Okay, it represents subcell. It represents subcells. Okay, it is denoted by small l. Small l. Is that clear? So the value of L lies, the value of L is from 0 to n minus 1. You know what is n? N means principal quantum number, the value of principal quantum number, that is n. So here the value of L lies from 0 to n minus 1. Okay. So if I consider that n is equal to, let's say 3, n is equal to 3, then what will be the value of L? L will be 0 to 3 minus 1. Then that means the value of L becomes 0, 1 and 2. Is that clear? Okay. So you just remember, for L is equal to 0, the name of subcell is S subcell. S subcell. For L is equal to 1, the name of the subcell is P subcell. P subcell. For L is equal to 2, the name of subcell is D subcell. D subcell. For L is equal to 3, the name of subcell is F subcell. Just remember this much. Okay. For the value of L is equal to 0, the name of the subcell is S subcell. For L is equal to 1, that will be P subcell. For L is equal to 2, that will be D subcell. And for L is equal to 3, that will be F subcell. Okay. So these are the designation of subcells: S, P, D and F. Clear? Very good. Now how you represent these subcells we will discuss. Okay. Suppose I have already discussed about your principal quantum number. Suppose n is equal to, let n is equal to 2, let's say n is equal to 2. Okay. So if n is equal to 2, principal quantum number is equal to 2, I can ask you find the value of L, that is azimuthal quantum number. So L will be 0 to n minus 1. So that will be 0 to 2 minus 1. So that will be 0 and 1. 0 and 1. So for 0, the name of subcell is beta S. For 1, the name of subcell is P. Okay, still it is not been completed. You just mention the principal quantum number value 2 at the left side. So for 0, there will be S subcell. So name of the subcell is 2S. So 1 correspond to P. Name of the subcell is 2P. You have to mention this N over here. Okay. So the name of the subcell are 2S and another one is 2P. So indirectly if I ask, this is 2S, find out the value of N and L. So you know, in the left side this 2, this is your principal quantum number value 2, and for S subcell L is equal to 0. So these are the values of quantum numbers, principal quantum number and azimuthal quantum number. For 2P you can write down N is equal to 2, principal quantum number value 2, and L that is equal to, for P subcell you know, 1. Is that clear? For example, if N is equal to, I can say 3, then find out the value of L, 0 to n minus 1, 0, 1, 2. Clear? So for 0, the name of the subcell is S. For 1, P. For 2, that will be D. You just mention the value of N over here. 3, 3P, 3D. So 3S subcell, 3P subcell and 3D subcell. Easy? Clear? Okay. So now remember the number of electrons in a subcell is given by the formula, that is 4L plus 2. 4L plus 2 is the number of electron. Okay. For example, if I ask you calculate the number of electrons of S subcell, P subcell, D subcell and F subcell, let's say I am asking you. Okay. So this is number of electron, that will be 4L plus 2. Number of electrons in a subcell. For S subcell, if I ask you for S subcell, then tell me L value that is equal to 0. So number of electrons, that will be 4 into 0 plus 2, that will be 2 electrons are there in S subcell. If I ask you for P subcell, L is equal to 1, you know. So number of electrons, that will be 4 into 1 plus 2, that will be 6 electrons in P subcell maximum. Next, for D subcell, For d sub cell, I am asking, small d actually. For d sub cell, number of electrons, L value that is equal to 2 for d sub cell. So number of electrons, that will be 4 into 2 plus 2, that will be 10 electrons. Okay, and for F sub cell, L is equal to 3, and number of electrons you can get over here, that will be 4 into 3 plus 2, that will be 14 electrons, like this. Okay, very good. So now the third quantum number, that is your magnetic quantum number, or this is also known as orbital quantum number. Magnetic quantum number, it is written as M. It represents, particularly, it represents the orientation of electron cloud. Actually, the electron density moves in which direction? It represents its orientation. Okay, so for this purpose, I need to define orbital first. Okay, so again you can say it represents the orbitals. So orbital means it is that region. Suppose किसी तुम पिला मानकर मन करो सपोज आइसक्रीम पसंद, ओके, एंड सपोज हियर इज लॉट्स ऑफ आइसक्रीम्स. सो यू टेल मी तुम मानकर भिड कोड लगे जो आइसक्रीम थी सेट लगे. ओके, सो दिस ऑर्बिटल इज दैट रीजन इन 3 dimensional space where the probability of finding electron is maximum. That means we are moving towards the position of electron. At first main energy level cell, then sub cell, and finally we are moving to orbital where the probability of finding electron is maximum. We can't predict the exact position, rather we can get its probability, means chance of getting electron is maximum. Okay, the tendency of getting electron is maximum. So exactly it represents orbitals. Orbital means the 3-dimensional region around the nucleus of an atom where the probability of finding electron is maximum. Clear? It is represented by M. It is represented by M, small m. Is that clear? Next, the value of M that is equal to, the value of M lies minus L to 0 to plus L. Minus L to 0 to plus L. For example, I am saying, if L value is given you 2, then find out the magnetic quantum number values or its orientations. M that will be equal to minus L, that means minus 2, minus 1, 0, plus 1, plus 2. So how many orientations you see? 1, 2, 3, 4, 5. 5 types of orientations in 3-dimensional coordinates x, y, z axis. That clear? Next, if I write that L is equal to 1, let's say L is equal to 1, then what will be the value of M? That is minus L to plus L, minus L to plus L. Minus L means minus 1, 0, plus 1. Okay, so if L is equal to 1, then it has how many orbitals? 3 orbitals having 3 different orientations, -1, 0, +1. Okay, so now see, now if I consider n is equal to 2, let's say n is equal to 1, let's say n is equal to 0, let's say, oh sorry, n is equal to 1, principal quantum number value n is equal to 1. Clear? So what is the value of L? L will be 0 to n minus 1. So 0 to n minus 1, 1 minus 1 means this L is 0. Clear? So its orientation, if I need to calculate m, then m will be minus L2 plus L including 0. So this L is 0, so m also 0. M also 0. That means n is equal to 1 correspond to which subcell beta? That will be L is equal to 0 correspond to which subcell? S. Okay, so in left side you have to write its principal quantum number value, that is 1. So that will be 1s. So how many orientations it has? Only one orientation, that is 1s. If I consider principal quantum number value 2 beta, so calculate the value of L, azimuthal quantum number value. So L is equal to, sir, 0 to n minus 1. The 2 minus 1, that will be 1. 0 to n minus 1. 0, 1. Is that clear? So for find out the value of m that will be minus L2 plus L. So L value maximum, that is 1. So minus L minus 1, 0 plus 1. Is that clear? Here you see, if I ask you represent the subcells, so for 0 S subcell, for 1 P subcell, and value of n that will be 2S or 2P subcell. These are subcells. Subcells. Okay, then which one is cell? N is equal to 2 for L cell. L cell. So I can write this one just below it. L cell. For n is equal to 2. And what are cell? Consisting of subcells. So subcell correspond to your azimuthal quantum number, that is 2s and 2p. 2s and 2p are subcells. Now back to orbitals. Okay, orbitals, because cell consists of subcells and subcell consists of what? Orbitals. Okay, so these orbitals, that is the home of electron, you can imagine, home of electron. Okay, so this minus 1, 0, plus 1, these are the 3 orientations with respect to ordinate axes, x, y and z. So I can represent this minus 1 for px, this 0 for py, this 1 for pz. You can write this one px, py, pz, no problem. Okay, so x axis orientation along x axis, orientation along y axis, orientation along z axis, 3 different orientations. Then you mention the principal quantum number value 2 over here, because it should be everywhere. Okay, to px, to py, to pz. So there are 3 orbitals in p subcells. These are your orbitals. Clear? Next, if I consider for n is equal to 2, then you tell me n is equal to 3. Let's say n is equal to 3. Then you tell me what is the value of L? 0, 1, 2, 0 to n minus 1. So then tell me what will be the value of m? Maximum value of L? 2. So minus 2, minus 1, 0, plus 1, plus 2. Clear? Now for L is equal to 0, subcell is S. For 1, subcell is P. For 2, subcell is D. Mention the principal quantum number 3S, 3P, 3D. So these are your subcells. N is equal to 3, K, L, M. So what is the name of cell? M cell. M cell. These are subcells. Okay. So the value of M, that is minus 2, -1, 0, +1, +2. Okay, so for this, how many orbitals are there? This -2 stands for dxy orientation along xy axis. This -1 stands for dyz, 0 for dzx, +1 dx square minus y square, and this +2, that will be dz square. These are 5 d orbital orientations, 1, 2, 3, 4, 5 for n is equal to 3. Okay, then I have told you mention the principal quantum number value 3d, 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 3d and 3d. So what are the 5 degenerate d orbitals? These are energy same energy. These are known as 5 d orbitals. Okay, dxy, dyz, dzx, dx square minus y square and dz square. Okay, so now the number of electrons in an orbital is 2. An orbital can maximum contains 2 electrons. We remember, we will confirm in next topic. So right now you just remember the number of the maximum number of electrons in an orbital, that is equal to 2. Okay, so these are orbitals, not subcells, orbitals. Is that clear? So in order to calculate the number of orbitals, that formula is 2l plus 1. 2l plus 1. You see, for l is equal to 0, 2l plus 1, 2 into 0 plus 1, that will be 1. Yes, for l is equal to 0, only one subcell, that is 1s. We have got it. For l is equal to 1, tell me, 2 into 1 plus 1, that will be how many orbitals? 3 orbitals. In every case we have got 3, that is px, py, pz. Okay, so for l is equal to 2, that is for d subcell, 2 into 2 plus 1, that will be 5. 5 d orbitals are there, 1, 2, 3, 4, 5. Okay, for l is equal to 3, that will be 2 into 3 plus 1, that will be 7. F subcell has 7 orientations. F subcell have 7 orientations. I don't need to discuss over here because they are very complex in nature. Okay, even it is also not so necessary for your NEET and JEE point of view. Okay, so you just remember up to this d orbitals. Fine. So maximum electrons in an orbital, that is 2, and the number of orbital, that is given by 2l plus 1. So let us discuss about this shape of orbitals, shape of atomic orbitals. Clear? Shape of atomic orbitals. Shape of atomic orbitals. See, s orbital is spherical symmetry in shape. This is your x axis, y axis, z axis. Clear? So s orbital, you just put a football at the center. So here, this is s orbital having spherical symmetry. Okay, so this is spherical symmetry, s orbital, spherical symmetry in shape. Next, p orbital. P orbitals are 3 types: px, py, pz. You know, so very simply you can represent. Suppose px, this one is x axis. Okay, x dash. This is your y axis, and this one is z axis. So if I need to px, this will be px. Its slope lies along x axis, px. Is that clear? So two nodal planes are there. Two nodal planes. One is, you see, this one is x-axis, y-axis, and this one is z-axis. So nodal plane means no electron density. No electron density found. No electron density is found. Okay. So here, if this is lobes are lying along x-axis, then you see there is a plane like this. बीच में जो plane अच्छी, ठीक अच्छी, where electron density you can't get. This one lies this one and this plane I am saying. This plane. It is nodal plane. Okay, where electron density, lack of electron density is there. Next, py beta, tell me. This is x-axis, this is y-axis, and this is z-axis. Py means it lies, two lobes lies along y-axis. Okay, then the nodal plane is this one. It is caught at the center. Okay, one nodal plane. Then the x, py, and that one is pz. Pz, you can do like this: x, y, z. So this is pz. Okay, so pz is like this. So you tell me the plane will be on xy plane. This xy plane. This one is your nodal plane. Okay, where electron density is like. Then another one is dx square minus y square. So you can do like this. This one is your y-axis. This one is your x-axis. So this one. So these are the three orientations of p subcell. Next we will discuss about d subcell or d orbital. Next we will discuss about 5 d orbitals. Okay. So that is shape of d orbitals. You see 5 orientations d orbitals have I have told you: dxy, dyz, dzx, dx square minus y square, and dz square. Okay, don't take it headache because you just know the shape of orbitals. Okay, so first one is dxy. Suppose here this one is x-axis. This one is y-axis. Okay, so dxy, no need to draw z-axis, it will be confusion. So dxy means the shape of d orbital, that is double diagonal. I have forgotten to say the shape of p orbital was like this. This is a dumbbell shape. Dumbbell shape. Okay, and here the shape of d orbital, that will be your double dumbbell shape. Okay. Dumbbell, D-U-M-B, dumbbell, dumbbell shape. P orbitals have dumbbell shape and d orbitals have double dumbbell shape. This one double dumbbell shape. D orbitals have double dumbbell shape. This one is dxy. Similarly, dyz, you can say this is y-axis, let's say, this is z-axis, let's say. So this one will be your dyz. Okay, next another one remain dxy, dyz, dzx, x and z. Slope like this. This is your dzx, double dumbbell shape. Okay, so in d orbitals, how many nodes are there? 2 nodes are there, you can see. If this is zy plane, then a plane can be passed like this. This is a nodal plane which caught at the center, no electron density. By electron density will be observed in these lobes. Okay, so this one is one nodal plane and another nodal plane, you can tell me this axis. Here, ये बीच वाला plane where the probability is less, finding electron is less. So 2 nodes over here. two nodal planes in all these orbitals. Okay, so these are the shape of 3d orbitals. Another one is dx square y square, where the lobes are present over the axes. Okay, dx square y square means suppose this one is your x axis, y axis. Okay, so dx square y square means the shape of a double dumbbell like this. Lobes are present along the axis, dx square minus y square. Okay, don't be headache regarding this the shape of these orbitals, you just know it. Okay, next that is dx square dz square, dz square. Here nodal plane you just see one nodal plane here and another nodal plane will be here, two nodal planes. Okay, then dz square something different, that will be this one is let's say x axis and this one is z axis and this one is y axis. So here the shape of a d orbital like this and merged at the center. This is dz square. So these are the shape of orbitals, and forget about f subshell, f orbitals. These are very complex and you will go through their structure in your higher study. Okay, so right now you know about the shape of these atomic orbitals. Okay, clear. And the final quantum number, that was your spin quantum number. Okay, so spin quantum number, spin quantum number spin quantum number, spin quantum number. As we know, it is denoted by s. As we know, the electron's probability of finding electron is maximum in orbital. So in an orbital, electron spins around its own axis. Okay, so in an orbital, electron spins about its own axis, For example, this one is one axis and this one is, let's say, an atom, and if electron is moving in this direction clockwise, then the value of s will be plus half. If the electron is moving this wise, okay, so if it is moving this wise anti-clockwise and this wise clockwise, so right now if it is moving like in this direction anti-clockwise, here that will be, and here the direction is like this. So direction is like this. Okay, so if it is moving like this one, then value of s will be minus half for anti-clockwise. For anti-clockwise spin, s value that will be minus half, and for clockwise, this one is clockwise spin. For clockwise spin, the value of s that is plus half. Okay, and here another you just remember that is spin multiplicity, that is given by 2s plus 1, where this s is the summation of total spins. I will tell you how you calculate the spin multiplicity. For example, if suppose an orbital like this, 1 2 3, here is one electron, here is one electron, here is one electron. How many electrons are there? 3. So for this, every electron has same orientation. So for spin value, this one can be plus half, this one can be plus half, this one can be plus half. Okay, so here the total s that will be equal to summation of s, that will be equal to 1 by 2 plus 1 by 2 plus 1 by 2, that will be 3 by 2. Okay, so the spin multiplicity, that will be 2s plus 1, that will be 2 into 3 by 2 plus 1, 2 cancel, that will be 4. Okay, 2s plus 1, 3 by 2 total spin. So 2s plus 1, 2 into 3 by 2 plus 1, that will be 4. Okay. So if the number of unpaired electron like this is, let's say, 4, number of unpaired electron, if it will be 4, then tell me what will be the value of S? Half plus half 1, half plus half 1, that will be 2, total will be 2. So spin multiplicity will be 2 into 2 plus 1, that will be 5. That will be the spin multiplicity. Okay, so for today's class this much is enough. You just go through it. Quantum number is very important. Okay, so next class we will discuss few important rules, that is Horn's rule, Abba's principle, Pauli's exclusion principle. Then we proceed through electronic configuration of different element. Okay, hope you understand. Thank you for your kind attention. Okay, bye bye.